What's up, everyone? I'm gonna be doing another reaction video for a Simon DeDeo video. I've watched a couple of his lectures, which I think are really fascinating. If I remember to, I'll include some links to those. One on the topic of play, so he talks about just the concept of playing and what role that plays in our development of ideas, if I remember right. And another one where he was talking about the evolution of words. So like he did a study on what words were used in like some specific scientific journal in like the 1600s, and just analyzing the frequency of those words across many papers, across many years, and seeing how the words combined in frequency, like say gravity and earth or something, just for an example. Like there may have been a phase when that was in high frequency, and so he maps or graphs the results of the study and just talks about it, and it's really interesting in that talk. Anyway, this one's called The Unpredicted in Science, Literature, and Politics, which I thought had a fascinating title, and I really like listening to him, so here we go. I'm just going to get it started. It's an hour and 1 minute long, so I'll probably play it at 1.25. 1.5, it tends to be a little too fast in my opinion, but for me at least. But obviously it's a long video and I'm going to be talking throughout it here and there, so this video is probably going to be long, so if I can, I'll probably do 1.5.
It's obviously, if you are an academic yourself, giving a talk in front of your old thesis advisor is a nerve-wracking thing, because
Just make sure, okay.
Because I sort of expect, like, no, you shut it down, stop.
Shut it down.
But no, it's a huge honor to be here. I come out of cosmology, and in some sense, what I do now seems incredibly distant from where I began. But there is a common theme to what I do, which is that I tend to study things that are too big to do experiments on, that may have happened in the past, so you can't go back. So I'll talk a little bit about the French Revolution, which is something that, for better or for worse, only happened once. And as Chairman Mao said, it's too soon to tell what to make of it. So in one sense, I've traveled very far. In another sense, I have stayed, in fact, very close. And I'm probably the only person who has taught a psychologist to use the phrase cosmic variance, which is something I learned, of course, from David. And it's the error that comes not from a failure of your measurements, but from the failure of the universe to happen more than once. So there are limits to our knowledge that we can never overcome, and I bump up against them all the time. So, okay, so what do I do, right? I now study people. And when we first tried to study people scientifically, we sort of imitated what the successful sciences had already done, which is that we built labs and we put people in the labs like microbes, right? And we gave them problems that they could complete in 10 minutes, hopefully, and for reasonable amounts of money that fit into a junior faculty startup. What I learned from doing cosmology, and I guess it's the definition of cosmology, is like only work on the big problems. And what I'll talk to you about, or what I'll talk to you today about, is what people do when they do things that matter the most to them. What they do when they devote their lives to something. What they do, for example, when they choose to follow a career in science. What they do when they write literature and consume it. What they do when they tell stories that matter to them. What they do when they try to run their societies. And in general, what people do when they're passionately engaged in the business of life. A lot of physicists, when they leave physics, go into neuroscience, and neuroscience is a really lovely thing to do. I don't mean to knock it. But I will. No matter how complicated and how awesome your internal experience is, no matter how rich it is, we really only have basically two ways to get stuff from here into there, right? Until somebody on, I guess, the 7th floor of the Simons Foundation invents some kind of way to directly connect our brains to each other, we can either speak or we can write. And so the study of what we say and the study of what we write is not just a matter for humanities people to sort of look at and enjoy, but basically the only window we have, the only way we have to act on each other's minds. And to study what we say and what we write, we need tools that are commensurate to the task. And so I'll give you a little crash course in something called information theory. It's really fun.
I'd say a more universal term would be express. So speaking is one form of expression, body language is another form, whatever it may be. We're expressing what's in here externally.
But I should also say that the tools that I'll show you, the ways that we study how people talk and talk to each other and write to each other, these tools come from the engineering sciences. And if we think of people as sort of chips that process information, that take information in from other chips usually, right? Very few of the connections of a machine come from the outside. Most of it is internal, like in our societies. We spend most of our time worrying about each other and very little time worrying about, are we going to crash our car, right? But when we think of people as chips, we are in danger of making an assumption, right? Because when you build a computer, all these chips work together, right? This chip can't get something over on that chip by, processing information or concealing information, but this is entirely distinct from what happens in the human world. So if we were information processors, okay, we are information processors with misaligned incentives that makes us fundamentally different from machines. There is an idea that the economy is a computer. There's an idea that society is a computer. And if it is, it's in some only vague and metaphorical sense. So when I study people using the tools of the computer sciences, I do so not believing or fooling myself into thinking that they are designed machines created to cooperate. So I'm going to show you how to quantify the exchange of information between people. And that's a difficult task. It's difficult to figure out what's in somebody's brain. It's difficult to describe how people reason. And there's actually a really interesting reason why, which is that thinking is both something that we do and something that we aspire to do. Thinking is, and I use this image, this is a classic of Christian iconography right here. On the right-hand side, this is Mother Mary, right? This is sort of the ordinary person who thinks and reasons. And the only thing we know about Mother Mary, or the only thing we know about ourselves, is that we're disastrous at thinking. We have biases, we follow heuristics, we can, in some sense, this is how advertising works, right? It's basically getting you to reason poorly, and it's incredibly easy to do. When we put people in the lab and try to figure out how they think, we get a mishmash of results, half of which are contradictory with the other half. We have very little understanding of how people actually reason about the world. However, bizarrely enough, we do have a theory, a very precise and well-stated theory of how an optimal reasoner works, right? So if this is the human that we don't understand, this is what I would call the Bayesian angel, the angelic thinker with infinite capacity, infinite memory, the ability to process information perfectly. And in fact, we can describe the angel very well. So when I look at a social system, and I'll give you a bunch of examples in this talk, when I look at a social system, I'm going to be looking at it from the perspective of the angel, from the perspective of somebody who can think as long as they want and reason as long as they want. So how does this angel work? Well, it took us a long time to figure out what it meant to reason optimally. We had since the ancient Greeks, the idea of how to reason optimally in the case of what we call deductive logic, when we know things are true, right? So in high school, you might have learned to take a sentence like this, right? A is true and B is true, and transform it into another sentence that was equally correct. In this case, it's not the case that A is false or B is false. So these kinds of transformations you learn, and in fact, Aristotle knew them. We know how to describe them perfectly. We have had for many, many millennia now a theory for how to do it, but we had a lot more trouble with this problem, which is the kind of reasoning we mostly do in our lives, which is inductive, right? The kinds of things that people do when they go about their daily lives are not about perfect truths and perfect falsehoods, but about these things that are maybe true, right? So a statement in inductive logic, something like, most birds can fly. So I see a bird outside, and I say, well, most birds fly. So it's reasonable to assume this one will fly. And it took us, in fact, until the 20th century to figure out exactly how to describe that. In fact, many, many great intellects of that century worked on it. John Maynard Keynes, it turns out, tried to figure this out in his first book, and he got it wrong, unfortunately. I learned it from this guy. I'd never met him, E.T. James. He was the physicist who popularized this. And it turns out that there is an optimal way, just as there's an optimal way to take statements like this about perfect truths and turn them into other perfectly true statements, there's a way or a method, a mathematical system to take truths like this and turn them into other equally correct truths like that. It's called Bayesian reasoning, Bayesian statistics. And The only thing you really need to know about how Bayesian reasoning works is that it takes statements, it takes sentences that you might believe, and attaches probabilities to them. It transforms statements about things that you may or may not think are true into statements about things that have a certain probability of being true. And once you transform statements about what's in your mind into statements about probability, then you just kind of turn this crank and grind it and grind it. So I'll give you a really brief introduction to one of the aspects of this theory. It's a sort of fun part, right? So if beliefs are probabilities, then maybe we want to sort of weigh them, right? We want to sort of put them on a scale. And one of the things we might want to do is talk about how uncertain you are about the state of the world. And this is something that the physicists call entropy, and I will sometimes slip and call it entropy, but it's generally called uncertainty. So I'll introduce you to a short method for how to think about how uncertain you are about something. And I'll do it with this game, which you may have encountered, the game of 20 questions. So do people know the game 20 questions? Yes. Okay. Wait, I'm going to play this game. So 20 questions is you have two players, like you have the child and the parent, or the grad student and the advisor. The parent has something in mind, and the child has to figure out what it is. And the child can ask yes or no questions, right? And the parent answers yes or no, and the child has to ask the correct series of questions, or a good series of questions to get the game over really quickly, right? So we're going to play. Dave, will you play 20 questions with me? Okay. So I have something in mind. I guess now I'm the parent here. So I have something in mind, okay? And David, well, go for it.
Let's see, knowing the rules of this game, is it in Encyclopedia 7 to 13?
Okay, so this is why this man has multiple appointments at famous institutions. You anticipate me, David. So, in fact, actually, I will tell you exactly how you anticipate me. So this turns out to be a game that was played. This was a game show in Polish communist television, and this obviously, like, the free market is not operating, right, to shut this game down. And so, like the plumbers union would come and they play 20 questions. Like, okay, comrade, right, like let's play 20 questions, or whatever 20 questions is in Polish. I guess Maxime knows. So the plumbers union could have say, okay, is it, larger than a horse? Yes. Okay. Is it an animal? No. Okay. Is it a bus? Yes. Okay. Game over. Right? So this game went on until the Polish mathematicians unit joined, and famously, right, how do they play the game? And David anticipates it, right? They said, okay, does the first letter of the word you're thinking of fall in the first half of the alphabet or the second half of the alphabet, right? Okay, first half, right? Does it fall in the first half of the alphabet or the second half of the first half of the alphabet, right? And if you get 20 questions, right, and you ask it that way, you can actually split on the order of 1 million different things. And of course, there's far fewer nouns that we use in general language. So the Polish mathematicians, by asking a better series of questions, were able to finish the game earlier, and in some sense, right, then they had to shut down the game, right? And the Polish mathematicians had to emigrate, and I guess they teach at CUNY now. So, if you think about this game, right, in terms of like how to get it over as soon as possible, right, you're well on your way to the key quantity in information theory, the key way that we think about how to describe what's in someone's head. So let's just take an easy example, right? Let's imagine you're playing this against your father, and he can only think of 3 things, right? He can think of trees, birds, and cars. He thinks of cars half the time, and trees a quarter of the time, and birds a quarter of the time. If you want to end this game as soon as possible, what's the first question you ask? Is it living? Ooh, good, yes. So an equivalent question, right? Is it a car? But yours is just as good, right? Because trees and birds are living. So if the answer is no, then you know it's a car, right? So you get the same thing, right? Wonderful, right? So you guys are keeping up with MIT. I asked this question, I gave this talk in Colorado, and it was just dead silence. But it was a room full of historians, and I think humanists have trouble being wrong. So yes, right? You split on car first. Like, is it in the tree and bird group, or is it in the car group? So if the answer is yes, you're over in one question, right? If the answer is no, okay, you have a little bit more work, right? Because you have to now split between tree and bird. You can say, oh, does it fly? Or you can ask a question like that. But essentially, you have to split these 2 objects here. And so in fact now, okay, so half the time you have to take 2 questions, right? And so that means on average, right, if this is what's in your dad's head, right, or if this is what you believe about the state of your father's mind, right, the game is over in 1.5 questions, right? Now, amazingly, and I love this, right, you don't actually have to construct the tree to figure this out. You plug the only formula, right? You plug it into this formula. It's the formula for entropy, right? It's called entropy if you're a physicist. You take the probability of each of the options, right? P sub I for each of the options. Pi log pi, right? You add them all up, right? And then you always forget the minus sign. You put the minus sign in the front, right? And this measures the average number of yes/no questions, again, for that Bayesian angel, right? Or Polish mathematician, if you will, right? That optimal reasoner with infinite memory and ability to think almost instantaneously, right? So the optimal reasoner, when faced with an environment with a certain distribution of beliefs, right? If he thinks certain things about the world, you can now measure his uncertainty, the number of yes/no questions that he has to ask on average, right? Each time might be different. Sometimes it's cars, so it's over quickly, but on average. So let's play. I promised you literature. So let's imagine you take this as Jane Austen. her book Pride and Prejudice, one of the great works of the English language. So imagine like sticking your hand into the book and pulling out a word. Right? So I have the word, and I'm now playing it with David, right, or somebody. How many yes/no questions, on average, does that Bayesian angel need to figure out the word I have in my hand? Sorry? How many yes? Yes. About 18? 18. So I'm going to give my powers of 2 here, right? So 20 questions is about 1 million, right? So if I go 19 questions, that's 500,000. If I do 18 questions, that's 250,000. Jane Austen's vocabulary is almost certainly smaller than 250,000. So 18 is probably too much. The answer, unless anybody, prizes. Oh, yes, see?
I would say 9.
You're killing me. 9.06. Now, okay, this is it's a little spooky. Maybe you're the Bayesian angel. 9 bits. So, okay, the unit of yes/no questions is bits, by the way, right? So 9 bits, right? And if you think about 9 bits for a second, that's actually kind of surprising, right? Because with only 9 questions, right? The first question you split 2 things, right? The second question you split 4 things, right? The third question 8. The fourth question 16, 32, 64, 128, 256, 512. It turns out. So how is it possible to get this game over in 9 questions? But the answer is on average, because physicists always take averages, right? So let's take a sentence from Jane Austen. Here's the first one, classic sentence. It is a truth universally acknowledged that a single man in possession of a good fortune must be in want of a wife. Now, if you look at this sentence, right, most of it is garbage, right? It is that, in, of, must be in want of. Most, like, these words we focus on, right? These are words that can take time to drill down to. But your first question should probably be like, look, is it one of those junky, what we call function words, right? So it's a very lopsided tree. Most of the time, this game is over very quickly. Is it a function word? Yes. Is it a determiner? Yes. Is it the? Yes. Done, right? Okay, sometimes, okay, to get to, acknowledge, maybe you do have 18 questions, but that tree is so lopsided. Actually, free paper idea, nobody's actually looked at the variance in the number of questions you have to ask. Just FYI, free paper. Okay, so here we go. Quick science. Jane Austen, that's Jane, Ms. Austen. The entropy, the uncertainty of her word choice is 9 bits. Let's take another great English writer, Virginia Woolf, writing just over 100 years later. Higher or lower uncertainty in her vocabulary than Jane? Lower. Anyone for higher? I see people are hedging their bets. The answer is, bizarrely, slightly higher, but in fact within error. I didn't put the error bar, sorry, Dave. Within error, okay, identical. Which is really fun, right? Because Jane Austen does not use the word X-ray, right? So it seems like Virginia has more things to talk about, okay? But as she's bringing in, she's talking about X-ray, she's no longer making these really fine-grained distinctions between the carriages people drive, right? Like Mr. Wickham drives a Mazda Miata, right? She's, like, things come in and things go out. So even though the vocabulary is very different, the uncertainty is actually very, very close, okay? So this is how uncertain we are. We're just about as uncertain peeking our nose into Virginia as we are peeking our nose into Jane, right? So now we're off to the races. Don't worry, this won't be on the test, right? Because I can talk about not just my uncertainty about something, but my uncertainty conditional upon you telling me something. So if I tell you, oh, I'm thinking of something and it's like it's an animal, right? By giving you that, I now enable you to construct a better tree. So I change your uncertainty. And of course, that's what a signal is. A signal is something that reduces or alters your uncertainty. The nice thing about information theory is you can prove that information never hurts, right? So if I tell you something on average, it doesn't make you more uncertain. Sometimes it can, right? If I tell you something, it can make you more uncertain, but on average, it doesn't. It's one of the nice little theorems that comes out. So let's go back here and look at the signaling structure, right? Sorry? So the question is, right, I'm talking about uncertainty, right? But implicit, when I'm telling you I know what's in your head, I have to have some model of how you're thinking, right? I have to have some model of the world and the kinds of decisions you make. So I'm going to skip the question about distributions because we're in the discrete case here. So in fact, I don't have to worry about, Gaussian versus non-Gaussian. I just have a discrete set of categories, so that's an easier one. But to remind you, right, when I say the uncertainty of Jane Austen is 9 bits, I mean the uncertainty for this sort of angelic optimal reasoner. And if I require the reasoner to be consistent, right, then in fact I know axiomatically the angel has to behave in a certain way. So this is under the assumption, the model I have here is of this sort of perfect person. Now, okay, look, in 10 years we'll solve it, right, and we'll have this great model of how to degrade the angel into a human, but we don't have it yet. So I think it's a crucial question. I'm going to show you how an angel now will read Jane Austen, right? So the entropy of Pride and Prejudice, right, you stick your hand in, you pull out a word, you have 9 bits, right? But now imagine that I stick my hand in Pride and Prejudice and I pull out 2 words, and I tell you the first word. By telling you the word that came before the one you're meant to guess, right? I've given you some information. So I say, like, look, guess the word. By the way, the word before it is the.
1.5 times.
Right? Then I've helped you, right? I've given you some signal, right, of what's going to happen. So I can measure that. I can measure the reduction in uncertainty from knowing the word that came just before. And the answer is, right, well, so if I tell you the word before, my new uncertainty is 5.41 bits. Another way to say it is telling you the word before gives you 3.65 on average free questions. Right? So what I can talk to you now about is the signal structure, how information is flowing through a sentence of Jane Austen. I have my slide for this, right? So there you are listening, right? As you listen to somebody, right, your uncertainty is dynamically changing. What's this person going to say? Halfway through a sentence, right, you have a better idea. And in fact, a colleague of mine at the University of Arizona does this a lot. We often secretly put in signals in our sentences to help you see what's going to happen next. And we do it more in noisy environments. It's a fun story. All right, let's do some more science. This is great. I got called science. So, okay, Jane, entropy 9 bits, right? The mutual information, the amount of signal from one word to the next is 3.65. Here's Virginia Woolf. The entropy, you now know the uncertainty of her vocabulary is about the same as Jane's. Mutual information, higher or lower? Lower. Well done. It is. In fact, now it's very significantly lower. Virginia Woolf is much less helpful to you. 1 question less helpful. And this is like this basically equivalent, but this difference here is telling you a great deal about how these two women write, the ways in which they construct their sentences. Jane, in some sense, what this is taking up, I want to look into, is that Jane's writing, right, Ms. Austen's writing is conversational. She invented something called free and direct style, which is where you hear someone talking and you're not quite sure if you're overhearing their thoughts or you're being presented with the narration itself, right? It's a very free-flowing style, like almost drawing room style. Whereas if you read Virginia Woolf, it's much more angular, it's modernism. It's much more experimental. So what she's done, what Virginia Woolf has done, is selectively destroy signals, make her work less predictable from moment to moment. All right, so that's one word signaling another. That's an internal signaling structure to the system. Let's ask another question, right? Like, let's ask how a word can signal group membership, right? So you want to learn something about the kind of person someone is, what they believe or what they want you to think of them. Begin with this speech. I want you to tell me, this is a speech taken from the party manifestos, they're called, right? The sort of documents that are released after the convention for each of the parties. And I want you to tell me, is this a Republican or a Democrat? This is what we want for America, real prosperity that reaches beyond the stock market to every family, small business, and worker. Democrat. An economy expanding as fast as American enterprise and creativity will carry it. Free from unnecessary taxes, regulation, litigation. This is what we want for America, the restoration of self-government, breaking Washington's monopoly on power. The American people want their country back. What year is this? 1992. These signals have been around a long time. Actually, somebody I heard, you almost ruined it for everybody, somebody guessed it was Republican. I'll tell you exactly why you know it's Republican. It's this phrase, small business. Small business is an unbelievably reliable signal. The corresponding signal for the Democrats? Close, working families. Small business, working families, right? And those signals, actually, those were created in the 80s, okay? So now what we're talking about is not about how this word is signaling the next, right? Because Republicans, Democrats, this is not great literature, right? They're basically speaking normal English, or rather normal political English, which is a sub-variety, right? But now we're asking, okay, when we say words like small business, right? If I just turn on the radio, small business, and I turn it off, well, I already know who that person is, right? So we can now look at the strength of these signals. When are these signals created? When do parties distinguish themselves from each other? When do they use language distinctively? We can plot this over the course of the last half century. On the x-axis here is year. You live through these, right? On the y-axis here is this what's called Jensen-Shannon distance, just mutual information, right? It's the strength of the signal that to distinguish the yes-no question, are you a Republican or are you a Democrat? And so you can see that there's an interesting structure here. Sometimes the parties are very distinctive and sometimes they're not distinctive at all, or they're much less distinctive. I'll just highlight a couple of these. What is this period here, this maximum distinctiveness, the most distinctive we've seen the two parties? What election was that? Barry Goldwater, right? The second nuttiest president in living memory, right? Down here, what is this moment here, the least distinguishable point? Right, the Reagan era. Right? How did Reagan win? Right? Selectively destroying the signals that distinguish the parties, the Reagan Democrats. So these tell us a story about how people communicate. In fact, I grew up in the UK, so I can tell you a story, so we can also run this, right? Because this is now, it's not quite the unified field theory of social behavior, right? But it allows us to compare. I can talk about Jane Austen and Virginia Woolf. I can talk about the Republicans and the Democrats using the same units of bits, right? Here I'm just comparing the Tories and Labor, right? The distinctiveness of those parties, right? To the United States, right? So here, if you look in the 1980s, right, while the Reagan Democrats were having their heyday, Margaret Thatcher was causing riots in London. I remember the poll tax riots. Lots of math. But essentially what you do is you transform a text into a probability distribution. So you describe somebody's uncertainty about the text. You don't know what word they're going to say. You attach probabilities to it. Say, how uncertain am I about the words coming out of these parties? And how does my uncertainty change when I tell you the name of the party? It's like, oh, it's a politician. What's he going to say? Well, I'm about, I got 9 yes-no questions, right? They say, oh, he's Republican. Oh, he's Republican. Then I have actually only, 8 questions. I can build a better tree because I know that they use language distinctively. And that difference, that's the distinctiveness. So these are built off of the...
This is what I love about this guy's research, is his study of word choice. That's just happens. It's just organic in the way that we live. I find it interesting that this plot, I'm wondering if if this is balance, if there's a center point with two sides that are off balance in essence, and if you're off balance, you're to one side or the other, and the more off balance you are, the more higher up in this chart you go. I don't know if that's what's happening, because he's saying this is the degree of difference between the two parties in the word choice, the strength of the differences being used, of the words being used?
Party manifestos. So the text that they've released. There's a really good question, right, which is, this is not the only communication channel, right? So, Reagan is... Oh, yeah, exactly. But lies have structure. That's why they work. It's all about structure, right? In any case, right, so after, Margaret Thatcher blows up Britain, right, things actually calm down in the Tony Blair era, right? So Tony Blair basically does to the Tories what Reagan did to the Democrats, right? Gets the minimum signal distance. That's how he takes over the country, New Labor, in the same way that you might describe Reagan as New Republican. Okay, so you know how signals work. You came here to learn about surprise and unpredictability. So let's go back to this, right? You're playing this game against your father. You build this tree. You have this optimal way to gain information about what's in your father's brain, right? Your dad's thinking about something. Here's this distribution. You build this question tree, right, to get the game over as soon as possible. Now let's imagine you play against your mother. But you use your father's tree, right? And your mother, let's say, has a different distribution, right? So your father's an Uber driver, so he thinks about cars half the time, right? Your mother is an ecologist, so he thinks about trees half the time. So if you use your father's question and answer tree with your mother, it's no longer efficient, even though your mother is just as uncertain as your father about what she's going to say, right? If you use the wrong tree, if you're expecting your father and you get your mother, right? It's a question that sounds like you'd be asked in therapy, right? But if you're expecting your father and you get your mother, your tree is no longer optimal. Instead of getting the game over in 1.5 questions, it now takes a little bit longer, 1.75 questions. Turns out you don't have to construct the trees to know this. You compute something else called the Kovac-Leibler divergence, right? And essentially what it tells you is if you expect one thing, if you build your model of the world based on one reality and you encounter a different reality, okay, you'll no longer be an efficient question asker. You'll no longer have an efficient model, and this tells you the extent to which your model fails, right? So in fact, there's some really lovely lab tests of Kovac-Leibler divergence in action. People have tested how this works in the eye. So for example, if you show people a video, like a set of moving images, right? So here's, and they did 3 different videos here, right? So you show them a video. You can measure the uncertainty of different patches of the video, which is just like, oh, is it going to be dark or light, right? You can measure the uncertainty of the entropy. But you can also measure the surprise in the video at each point. And the surprise is different, right? The surprise is I build a model of the video for, let's say, 3 seconds. The kinds of pixels are in that patch, right? Are they bright or red? Or are they dark and blue? Build a model. And then I wait 3 seconds, and I see how much the model has changed, right? And the difference between those 2 periods of time tells us how surprising it is, how much a model built for one period will fail for the next period. And in fact, what you can see, so this is a surprise, this is this quantity here measured on the video screen, and this is an eye tracking device. And you can see we're hungry, at least at a very low level, we're hungry for the things that we don't expect. Our eye is guided towards the places in the world that violate the model we built. It's a very noble thing, right? I mean, like your eye, right, this very low level function, right? Your eye is sort of the opposite of like the Facebook, filter bubble, right? Your brain is constantly seeking the things that will disconfirm what it believes, almost like a scientist. Yes? Oh yeah, it's probably to survive, right? It's like, yeah, things are pretty cool, but then like, my model over there is like everyone's sitting still, but somebody starts coming towards me. I want to check that out, right? So that's how our lower level mind works. Let's go a little bit up the scale because I promised that I would talk to you about things that matter, right? I don't have the lab space to look at someone's visual system, but let's ask not how the eye is attached to visual novelty, but how the mind is attached to much more rarefied forms of novelty. So I decided last year I wanted to study mathematicians. This is this lovely book by Michael Harris, who's a mathematician at the Institute for Advanced Study. Mathematicians, they're completely bizarre creatures, right? They're very different from scientists. Here's one way you know. A French sociologist studied mathematicians, did a survey of how they understand themselves. 62% of pure mathematicians chose this description out of some very large collection, like 20 possible descriptions. Mathematics is a very pleasurable sort of game with the appeal of the unknown. So I wanted to study mathematicians. They were less organized than I would have liked, so I studied string theorists, so like sort of cheaper mathematicians. What I did was I took all of the papers that had been published in string theory over a course of about 10 years that were put on the preprint archive, right, which is where we publicly share, physicists and other scientists publicly share what they do. Right? And I can make fun of string theory, but I'm running out of time. What I did was I took each of those papers, and I did what we did with Jane and Virginia, right? I turned it into a probability distribution, right? So I said for each of these papers, put your hand in the paper and plot a word, right? Built a model of the patterns of word usage. In fact, we did it on a couple different levels, but I'll just talk about the sort of basic ones. And then we can say, look, okay, so you encounter a paper written at a certain time. How surprising is it given all the papers that occurred last month or 6 months ago, or a year ago, or 5 years ago. Right? And if I transformed them into this sort of Bayesian picture where a paper is just described by a probability distribution over words, then all of a sudden all of this machinery comes in for free, and I can make the same measurements on the string theory archive that the visual studies people at Irvine could make on where people look. So using this KL divergence, you encounter a paper at 1 month, right? Having trained on the previous month's papers, I can tell you that month to month, string theory is pretty stable, meaning the amount of surprise, right, that you see from 1 month to the next is pretty constant over the 10 years. Right? You can think of it as sort of the Brownian motion of science. Right? Interestingly,
well
string theory is
said.
slowing down. So if you look, for example, on a 3-year time scale, back in 1996, right, it was more surprising if you look 3 years back, right, than if you look 3 years back in 2002. So if you think about like papers being written, if this is like the space of all patterns of word usage in string theory, like things are bouncing around and they're kind of drifting, but that drift is kind of stalling out. And string theory seems to be slowing down. Another way to say it is 5 years forward is equal to 2 years back. You have to wait 5 years to see as much drift, as much change in string theory as you did looking backwards in time. So if we measured how surprising an article is, how surprising somebody's paper is given what came before, right? At some point we sat there, and this is work I did with my graduate student Alexander Barron, right? At some point we decided, well, if you can measure how surprising something is given the past, you can also measure how surprising something is given the future. So what does that mean? Right? If you're surprising given the past, it's like, oh, like no one ever did that before. Like how novel, right? We had a sense of what that was, but then we said, well, look, we can just flip it, right? We can do the obvious thing and measure surprise going forward. What does it mean to be surprising given the future? If you think about that for a moment, it's like, wow, like what you've done, it doesn't really look like the future, right? Which is not something you want to hear, if you're like finishing your PhD, right? You don't look like the future. It's also a threat that you might get in New Jersey, right? I don't think you're going to be seen around here anymore. So on the x, each of these points here is a paper, a scientific paper. On the x-axis here is the surprise given the past. Alexander and I call that novelty, right? On the y-axis is surprise given the future, and we call that transience, right? Transience is like, oh, you've done something, but it doesn't really look like what's going to come next. It's a transient moment, right? So using some of the high-powered statistics that I learned from David, right? These covary very strongly, right? So what does this mean, right? Like, the first law, right, of unpredictability, like what is new is quickly forgotten, right? Like, no one's ever done that before, and no one will ever do it again. I have a friend of mine who an engineering major at MIT, and she became a science journalist. And people for a while, everyone wanted books on innovation, right? I gotta write a book on innovations. I hate this word because when I was at MIT, innovation was a bad word, right? It was like, here's my problem set. How innovative? No one's ever solved this calculus problem like that before, and no one's ever going to solve it like that again. So obviously, it doesn't end there, right? Because now we look at that scatter plot, and yeah, it's very strongly correlated, but it's not perfect. So like, look at this guy here. Look at these points down here, right? They're really novel. They're really new, right? They're using words in a way that you haven't seen before, right? Or that are deviating from the standard pattern, right? But like, given where they are on the x-axis, they're not as high up as they should be. And so we look at those points, and here's one of them, total classic. I'm sure you've all read it. Renormalization of quantum field theories on non-commutative RD, volume 1, scalars. That is 101 citations. Right? Given the particular era in which it occurred and the field it's in, that puts it in the top 5% of all cited papers. And in fact, it so turns out that this sort of cloud, this clump down here, right, is where almost all of the citation classics come from. We can plot it this way. How much more surprising, let's say you read a paper and it has an above median number of citations. And as you know, in academia, right, most things don't get cited very much. So like above median here, it turns out to be like more than 3 citations. Right? But how much more surprising are above median papers, right? And so if you look at this, right, the relative date, so if you publish at T0, right, and you publish a highly cited paper, it's more novel than the low cited papers looking backwards, right? But looking forwards, right, it's more surprising, or sorry, less surprising given the future, right? In fact, like, this tells you exactly how to write a highly cited paper, right? It sort of peaks here like around sort of minus, 3.5 years. So if you want to write a highly cited paper, do something different from what people were doing 3.5 years ago, your payoff will come, right? Your payoff, your influence will hit about 2 years later, more or less. Okay? So if the first law, right, is like what is new is quickly forgotten, right? The second law, at least in this system, is that it picks, right, physics or science selectively predicts or picks the most surprising material and gives it this sort of external honor of citations. And of course, if you're a scientist, you know, like citations, you live or die on your citation record, at least for lesser institutions. So, when I was thinking about, especially string theory, which people are now saying is a game without rules, right? I thought about Calvinball, right? And this is sort of the generic problem that we have when we try to figure out what people do when they're not being given incentives, right? Like, help people buy and sell. This is interesting, but I don't think that interesting. Right? When people do science, they're not motivated. They're not really motivated. No, we don't win a prize, right? You're not motivated by prizes when you do science. Those people who are tend not to do very well, right? But if it's just a big game that we're all having fun in, right, what stops it turning into Calvinball? So Calvinball, this is a game, so people know Calvinball from Calvin and Hobbes, right? So Calvin, Calvin is this little guy here, right, and he has this imaginary friend, a tiger, and they play this game called Calvinball. And the problem with Calvinball, the joke about Calvinball, right, is that the rules change just as fast as the game itself. Like each rule, as soon as it gets invented and used, is replaced by another rule. So no rule is invented more than once, right? The system, in some sense, has no inertia. Well, so that's the thing, right? So what stops it, right? In some sense, there is basically, well, one way to think of it is that there's sort of two strategies to scientists, right? You either are the sort of inertia-preserving people who write papers that are very similar to other papers, right? So you're not novel given the past, right? You're kind of in the mainstream, and you're rewarded by not being forgotten, right? Like, yeah, what did I do? I did something. I wrote a paper on dark energy. Like, yeah, a lot of us did, you know? Good stuff, right? Or you can take the high-risk strategy, right? And you can say, look, I think something no one's ever seen before. And the joke is, it's easier for me to distinguish a highly cited paper from a low-cited paper. It's easier for me to make that distinction than it is for me to make a distinction between a highly cited paper and a crank paper, right? It's harder for me to tell the geniuses from the cranks than it is for me to tell the geniuses from sort of what Thomas Kuhn would call normal science, right? So the question of why an activity like this doesn't sort of destroy itself, right, sacrifice itself on the altar of novelty, right, is in some sense a story about how people create institutions to preserve it, how we reward selectively. And it seems like there might be some process or some set of strategies that people have learned to adopt. All right, so from string theory, we will go to fan fiction. Has anyone written fan fiction? Okay, fan fiction is a bizarre thing. I say bizarre. This is work with Yishi Jing, who's a graduate student at Indiana. So fan fiction is people watch. There are people who have written fan fiction. You're hiding. Okay, people write television shows. They create stories. They write Pride and Prejudice. Right? People read these. They fall in love with the stories, and they write new stories based on them. Right? And this, once the internet hit, became unbelievably mainstream. It started off as what's called slash fiction. Slash because it was often these stories were often pornographic. So a lot of slash fiction was originally written about Star Trek, and so you would, in the title, you would tell people who the couple was going to be, and the most popular couple was Kirk/Spock. Most of this is actually written by women. It's mostly written by women who do not attend college. I years ago interviewed some of these people, and one of the first things I'll tell you is that nobody writes pornography for women. It doesn't appeal to us, so we wrote our own. Yushi brought me this database. She said, I have 93,000 short stories in it. And I'm like, that's great. That's about as many quasars as we had in the first data release of SDSS. She said, no, not overall. 93,000 short stories based solely on this one television show. 93,000. There's an enormous amount of creativity, of writing, of effort, of storytelling that people have done, right, in the service of continuing the stories they love. One of the most popular, it's bizarre stuff, just so you know, right? So one of the most popular story arcs when people write fan fiction about Sherlock is male pregnancy. So what happens if, like, Watson got Sherlock pregnant? Okay. In fact, a lot of fan fiction is kind of beautiful. So and it's mostly straight women, why are straight women writing essentially homoerotic fan fiction? One of the stories that people tend to tell is that they like relationships with some level of equality in them, right? So if Sherlock's this super genius, well, what's it going to be like if he has to have a child? Right? So look, if string theory is fan fiction about the natural world, right, we can do the same thing. In fact, the nice thing about this is that these new sites, they don't have citations, you don't cite each other, but you have something called kudos. So if you like something, you give it kudos, right? And so usually ran essentially the same analysis on fan fiction, right, as we did on string theory, Alexander did on string theory, right? And what she found was essentially the opposite trend, right? So whereas string theory rewards, and I'll walk you through this, whereas string theory rewards, right, things that are novel with high citations, right, the more you deviate from the mean, right, the more possible it is to, right, get a highly cited article. Fan fiction works the other way. It's an inherently conservative process. So the articles that get the stories that get the most likes, right, are actually closer to the mean. It's a much more conservative process. That sort of makes sense. Right? They're telling stories about something they love. If you deviate too much, you're no longer telling a Sherlock Holmes story. It's no longer part of the genre. So I'll just talk about this briefly. Right? I gave this talk, and of course this always happens when you do social science. Someone says, well, obviously, why did we even pay you? I could have told you that, fan fiction was conservative. Well, okay, fine, wise guy, who's not here. She was a woman, my colleague. She was just causing trouble. How does poetry work? So Jenny and I, so this is another one of these superstar undergrads, right? So Jenny, we went and we scraped all of Poetry Magazine. Poetry Magazine is sort of the premier journal of poetry in the United States. It's really easy to find critical works that say the history of Anglo-American poetry is identical to or indistinguishable from the history of Poetry Magazine, right? So this is sort of, in some sense, the canonical place that poems happened. It's T.S. Eliot's Inner Love Song of J. Alfred Prufrock, Sylvia Plath. Like everybody you know is in this journal over the last 100 years or so. It also has unbelievably crap poetry. This is the first poem that's in Poetry Magazine. It's a poem about poetry, which is already a bad sign. I just encourage you to read. It's just so awful. And it's amazing to me, like, you read it now, and you're like, it's like right next to, like, the love song of J. Alfred Prufrock. How did they not know, right? So Jane did this very clever thing, right? We don't have citations, right? But of the 26,000 poems in Poetry Magazine, 72 of them make it into the Norton Anthology, which is like the standard canonical text that are taught to college students. And so the question is, what are the properties of those poems that make it big? So I ask you, right? Is poetry like string theory? Right? Are the things that make it big rewarded for their novelty? Or is it like fan fiction? Are the things that make it big the ones closest to the standard? Trick question, as always. It flips. The beginning of the century, the poems that get canonized are incredibly innovative. Ezra Pound, T.S. Eliot, these guys look nothing like what's around them. Okay? Somewhere in the post-war era, two things happen. First of all, there's this enormous burst. Right? The system becomes incredibly disordered. Right? It's almost like it melts. It goes through some phase transition. Right? Things go bananas. None of the poems look like anything. It's also this incredibly creative burst is where the majority of the canonized poems come from. After that burst is over,
this guy's involved with complex system studies, and I love that he keeps referencing these dynamics from outside the system. To say it's almost like it melted it's a great statement. I'm not sure what exactly he's referring to about this that is like that, but that is a true thing that we can draw parallels to, is these phase changes and things of that nature, but in a way such as this, and not just in just a purely physics like melting water kind of thing, but in taking the physics of melting water or of anything melting and applying it to systems like this and seeing the parallels is a way to shed light on things. And I really appreciate that he more than once in this video has made a statement like that. I forget the other one, but kudos to him.
System appears to have frozen. And in fact, now poems after 1970 that make it into the anthology are actually closer to the mean. So poetry basically switches incredibly disordered. Right? It's almost like it melts. It goes through some phase transition. Right? Things go bananas. None of the poems look like anything. It's also this incredibly creative burst is where the majority of the canonized poems come from. After that burst is over, the system appears to have frozen. And in fact, now poems after 1970 that make it into the anthology are actually closer to the mean. So poetry basically switches from this kind of investigative, surprise-seeking mode, right, into this kind of fan fiction, genre-confirming mode, right? So if you think this is a story about the collapse of poetry, like I would agree. I'm going to show, well, let's see if we have time. I will show you briefly. Here's just a sort of trajectory. These are just kind of zoom in at the micro level. Here are two poems published in the same issue. A poem by W.B. Yeats, which is an unbelievably good poem. It's in the Norton Anthology. And then kind of like a test case poem. Like this is like an O-star poem, right? It's just totally forgettable. And again, you look at these, right? And this one is just a great poem if you have any taste in poetry. And this one is just clearly just a terrible poem, right? Okay. And you can look at the trajectory. So what I'm plotting here, this is the year, right? So the poems are both published in the same year, just before the war, right? This red line is the similarity of Yeats's poem to the poems of that year, right? So you'll notice that it's really low if you look backwards, right? The canonized poem is much less similar to the past, just like the highly cited string theory poem. This is a poem in the sort of early phase, right, of American poems, right? And you compare this, right, to Ross, right? Ross is writing essentially in a way that was sort of big 10 years beforehand. Right? Yates writes the poem, and in fact, about 10 years after, his influence peaks. Right? Ross is already on the way down. Interestingly, both of them get forgotten in the 1960s. No one writes like either of them. And now you can see Yeats coming back into fashion. So it's sort of zooming in on a particular arc. I'm going to skip over this. I'm going to go over my great astronomy metaphor, and I won't even tell you about the French Revolution. Because I want to get to this question.
No.
Okay? You know, so far I've told you, right, the talk was, you know, unpredictably, where novelty comes from. So it's sort of zooming in on a particular arc. I'm going to skip over this. So it's sort of zooming in on a particular arc. I'm going to skip over this. I'm going to go over my great astronomy.
I wish you would just
Metaphor. I won't even tell you about the French Revolution. Because I want to get to this question. Okay? You know, so far I've told you, right, the talk was, you know, unpredictably, where novelty comes from and what we do when we get it. Well, I've only told you what we do when we get it, right? I told you the string theorists like it, right? The fan fiction writers hate it, right? And the poets used to like it, and now they've come to hate it. But where does newness come from? where do these great ideas come from? Where do the things that haven't been seen before and yet persist? Where do they come from? So if you ask an academic, right, the standard story is like, look, we get together
Yeah, I
and we
wish you
talk it
talked
out,
about
and
that.
so this is a great, right? This is the origin of quantum mechanics in Brussels, right? This is one of the great conferences, the Solvay conference, right? And so we have this idea that to get great things from the world, right, we have to get along. If you look at our most successful institutions, however, it seems that they have selectively chosen not to do this. Right? If you look, for example, at the free market, and for all of its failures, it does seem to work better than communism. Right? The free market is a conflict-ridden system. People succeed and they fail. Right? You don't get picked up off the ground unless you're too big to fail, I suppose. Right? When we have an election, right? Somebody wins the election and someone loses the election. It's very un-Quaker. You're a scientist. You have this peer review. This is an article I wrote with a graduate student at the time, one of my first articles after I was a postdoc. I'm not meant to show this, right? So we wrote this article, very proud of it, right? This is the peer review we got, right? This is devastating, right?
Nah.
I still remember this day. Right? You shouldn't really show your peer reviews. Right? It was really easy to figure out who wrote this review, and we're now friends. And the article was not a good article, and we got this peer review, and he totally trashed it. We wrote a better article, right? But this is not friendly, right? This is not let's get along, let's help each other. This is just crap. Just blow it up, tear it up. Right? So science is sort of fun and cooperative, and we play and we laugh, but it's also disagreement and conflict. And we build in structures to science, like this is anonymous, right? I didn't know who this was. In fact, the person who wrote it didn't know who I was. Right? He actually sort of later we figured out who we were. He said, God, I thought you were like this old famous guy in Chicago. If I knew you were kind of this young guy just starting out, I wouldn't have been such an asshole. Right? Which I didn't like that actually, because of course, like, we're meant to judge each other in this very clean way, right? We're meant to be able to say, no, that's why we blinded. Right? In the humanities, they even double blind, so you don't even know who wrote the article. Right? Also in computer science sometimes. We make it possible for people to disagree violently without harming each other. Right? In the same way that you might say democracies allow people to disagree without revolution. So, the question I have is, what is the relationship between the creation of novelty, and in particular the creation of persistent novelty, the new stuff that sticks around, which is as good a definition of creativity as I can come up with, right? What's the relationship between that and conflict, people disagreeing, right? In order to get along, in order to produce, do we have to get along? So I can't actually look at everyone's peer reviews. I would love to. I can't, but I actually have a different system where we have a similar kind of process, which is Wikipedia. Wikipedia, the encyclopedia that everyone can edit. And what we can see is people producing an article and altering it over time. I can see how much the new version differs from the old version, right? And I can correlate that with the levels of conflict that are in the system, okay? The most edited article on Wikipedia still today, does anyone want to guess? You might know if you've heard me talk about this. Middle East, close. Close. God is there, global warming is there. The most, George W. Bush. 45,000 edits, and actually this is different from cosmology, because when I started there were only 42,000 edits. So I get new data to test our theories on. So there are 45,000, I mean there's 45,000 different versions of this article. And what I can do is I can say, great, like here's sort of the EKG of surprise, right? So this is sort of over time as the article's being written, right? Here's how surprising a version is given the one just before. It's kind of a mess. We alter the time scale, things come into focus. And now we say, okay, how surprising is the current page given the 1,000 versions that came just before? And now what you see is this really amazing structure, right? Where it's kind of, page kind of people are editing in it, and then pow, right? Something happens. Decays. Pow, right? You see these sort of introductions. This one's really clear, right? Someone did something, pow, changed the page, and then it sort of slowly decays as the new version persists. Sort of like a Thomas Kuhn writ small. So what are these little bursts? Like, are they real bursts? And the answer is yes. I mean, so you see this and you're like, is it really real, right? So you actually go and you look. So I'll show you just very briefly. Look at that first burst there. So we'll take the page just before, right, and the page just after. On either side of that sudden burst of surprise, right? So something happened there. What happened, right? And in fact, if you look, and I won't show you the page, it's already gotten really long and it's really tedious to read, but there's the page before, here's the table of contents before, and here's the table of contents afterwards. And essentially most of it's still there, right? It's kind of moved around a little bit. But the big thing that's introduced now is that the Wikipedians have decided that their page is also going to describe all of these controversies about George Bush. Like, oh, you remember the drunk driving thing and the Air Force thing, right? And what they've done is they made this decision that Wikipedia, that page is going to become in some sense politicized. It's going to cover current events in a certain way. And whether that's good or bad, I don't know. I don't have a normative theory of what they should be doing. They don't have any idea what they're doing either, right? But at least what we can see is that these spikes are real, right? You always want to make sure that if you see, you have your great measurement, but is it really hooking into something? Okay. So you look at these probability distributions and you look at the KL. Yeah, now it gets a little trickier, right, because you can coarse grain in certain ways. So we do something called topic modeling, right? So there's different ways to look at this. Essentially what we're doing is we're asking how much does the pattern described probabilistically deviate from the one before, right? It's that same sort of underlying idea of pattern recognition and pattern violation. Right? So David said one of the most common ones is Israel-Palestine. That's true. How do I measure conflict in Wikipedia? Turns out to be pretty easy because there is a marker of when people disagree so much that in fact they start undoing what the other person does. So here's the Israeli-Palestine article, or one of the many ones, right? We can actually look at the history. Of course, the reason we can study this is because Wikipedia is an incredibly open system, right? It's completely transparent. Here's the history of the editing. I've just taken a little section here. So it reads up the page. That's how you read these histories, right? And you can see, right, there are certain moments, right, where something called a revert has happened. So if you look here, right, so on sort of 3 minutes to midnight UTC, Greenwich Mean Time, on 28th of November 2014, just a random moment in Wikipedia's history, right? On 20th of November, this user Schmooth comes in, and he makes an edit. I'm going to guess he's he, right? He makes an edit that says, I added a small paragraph explaining what the conflict is actually about, as the current article fails in this most basic of tasks. Like, what could possibly go wrong? Like, let me start, like, I'm going to just explain Israel-Palestine to you in a paragraph, right? And in fact, it takes literally 3 minutes before this user comes in here, Daniel J. Leivik comes in, and he says RV per MPOE. What he's done here, and this move from here, actually these two edits together to here, what Leivik has done is hit undo. He's undone. It's called a revert in Wikipedia parlance. There's another one up here as well, right? So these reverts, like the way to think about this, like say I'm working with David, right, and he's like, you know, Simon, great draft. I've made some edits, and I say thank you for the edits. I look at them, and I'm like, I've taken all of them out. At that point, David and I are in some sort of conflict, right? You had to write an introduction once, and if you write a sociology article, the introduction is like 10 pages. And so this is where we're in task conflict at that point, and then it turns out it's highly correlated with relational conflict. So we can now coarse grain the history of Wikipedia into this like string, this binary string of C's, which we call, you know, sort of constructive or creative edits, things that take the page to a new state, and R's, which are where people undo each other. This is the actual data from Wikipedia for the George Bush page. You can see, right, made an edit, and then the revert. It only took 3 edits on the George Bush page before someone got so mad they had to undo somebody else, right? So you can see there's this pattern here of how people argue. So the question is, what's the relationship between the distance to a revert, how close you are to one of those conflict points, right, and how innovative the creation is, how novel the page is, right? What's the distance to the conflict, especially between the distance to the conflict and the amount of innovation in that page? It turns out, right, it's disastrous. Conflict is really bad, right? The further you are, let me put it, the further you are away from conflict, the more novel, the more surprising the page is. So it looks like conflict is suppressing the creation of new material. Okay? I will not tell you exactly how we complicated this story, but it turns out that there are distinct patterns, this kind of a machine learning style analysis. It turns out there are distinct patterns or motifs that allow you to distinguish 2 types of conflict from each other. It's not in the overall level of conflict. It turns out, and just the patterns, are you the kind of conflict where you do RC, RC like this, or are you the kind of conflict where you do sort of pairs of R's like that? Those 2 conflicts are actually distinct. We call them type 1 and type 2. We built this model to distinguish them. And it so turns out that these 2 types of conflict have entirely different effects. When you're in type 1 conflict, okay, and it turns out there's the way you understand the kinds of conflicts people engage. When you're in that type 1 conflict, right, you call it sort of a cooperative or tit-for-tat thing. And that's like, I say, David, I've taken out your revert, or you're picking out your edits, and David says, you know what, I just put them back in. Oh yeah, well, I'll take them back out, right? That's type 1 conflict, right? Type 2 conflict is I'm like, you know, hey, David, how about this? And he's like, nope. Okay, how about this? Nope. Okay. So one is called rejected proposal, the other is sort of cooperative conflict. It turns out that if you're in, bizarrely enough, if you're in that kind of conflict where I'm like, no, Dave, and he's like, no, Simon, we're in that position of equality when we're rejecting each other, surprisingly enough, that is, in fact, incredibly good for innovation. So the closer you are to a conflict point when you're in that type 1 style of conflict, the more innovative you are. That signal's swamped by how awful it is to be in type 2 conflict, right? If you're in type 2 conflict, just nothing good happens. If you're in the type 1 conflict, it turns out the closer you are to the flashpoint, the more the article is changing. And in fact, the more the article is changing in a persistent fashion. So we can think of sort of type 1 conflict, right, as this sort of innovation mode that the system goes into. So is conflict good for creativity? Right? So I hate to say it, but the answer is like sometimes. There seem to be certain distinctive patterns of conflict that are associated with the production of something new and persistent. So I will leave you with the sort of the 2 open questions I see here. The first is, right, we gave you this series of associated with the
slow, lower conflict on average, equal fights, vandalism, rejected proposals.
Production of something new and persistent. So I will leave you with the sort of the 2 open questions I see here. The first is, right, we gave you this series of examples of systems, right? We gave you string theory, we gave you Anglo-American poetry, we gave you fan fiction, right? They process and respond to newness in different ways. The physicists reward the risk takers. The fan fiction people do not. And I guess the second question is this, right? If you want innovation, if you want new things, and in particular if you want new things that persist, what kinds of institutions can you build that put you in that kind of conflict that is productive, right? That in some sense selectively suppress conflict, right? You want peer review that works. You don't want to get rid of peer review. You want peer review that works. You want conflict between individuals, between businesses, between political parties, conflict that's productive and not destructive. I'll say one thing. We did a little analysis of I didn't show you the spike for the most recent presidential election. We did an analysis of the debates. And I'll tell you one thing, right? We have never seen two parties speak in such similar fashions. The distinctiveness of the two parties was at an absolute minimum, the smallest that we've seen in the history of the data we have, which goes back to the 1960s. So I'm thrilled to be here. I understand we have a little bit of time for questions, if we do. And thank you very much for joining us.
I love it. That's great. That was a great talk. Simon's Foundation. It's kind of unfortunate that they would disable comment. Oh no, they didn't. Okay, I was gonna say. Only 48 views. This is from 2017. Yeah, it was really interesting. Let's see. Thoughts. Not what I expected. It was unpredicted. But like other things I've seen of his, it's a in-depth study of something that's just... What I like about it is he finds something that is just already there in just the way that we do things. It's kind of like observing ants. Like what is being observed is just organically happening, completely oblivious to the observer. They're not aware of the observer. And so they're being themselves. And that's what we're doing when we're doing these things. We're not aware that someone's watching us do all these changes and all these things, and it allows us to organically create something that can be studied after the fact and learned from, even though that's not even at all the intention at any point in the process of creating that thing that's created. But he's extracting some information from something, from many things, by just studying the words chosen and the patterns that are there. And I mean, I really appreciate his work, and I highly recommend checking him out. As you can see, I just searched for him and I found this video, and that's why I'm watching it, because I thought it was interesting. So alright, I'm gonna end this. I'll be back in the near future. Thanks for dropping in. Feel free to subscribe and watch my other videos and learn some science with me and whatever else, Peace out.